I'm going to start with a screen share. Okay, should have seen these notes before, but I do want to go over these from chapter 4 because they are important. This is an important concept in stat class. Okay, so let me go over these. Let's see, there it is. And so what we have in chapter 4 and the rest of the chapter, and in fact, the rest of the semester, we're going to be using an idea someplace in there. It might not be directly like we have in this section or in the next chapter, but it is the idea of a probability distribution function. Now, there are two types of probability distribution functions based on what we call a random variable. A random variable is a numeric outcome. If it's not numeric, it's not a random variable. So it's a numeric outcome from a probability experiment. So a probability experiment is just a process you do the same way over and over again, like toss a coin 5 times. That would be a probability experiment. Okay. Say ride your bike 10 miles the next 7 days. That would be a probability experiment, and then record the time. That would be a probability experiment. Okay. A discrete random variable has countable number of outcomes. That means I can count up the outcomes. So in other words, I can count how many customers are in line in the checkout line at Meijer at noon. Or I can count up how many students are in the class at any given time. Okay. Or how many airplanes land at the airport by 1 a.m. That would be a discrete random variable because I can count those up. A continuous random variable means the outcomes are not countable. They're uncountable. There are so many outcomes, every single one is filled in. So for example, a temperature, or the distance you travel, or how tall you are, or how much you weigh. Those would be continuous random variables. Now, what is this idea of a PDF, and how does it tie in with the random variable? Well, a probability distribution function has every random variable value that it can take on for a probability experiment, along with the corresponding probabilities. So for example, here's a probability distribution function. X always represents random variables. That's the variable we use for random variable. The outcomes are 0, 1, 2, 3, and 4. Beneath these, you have the corresponding probability. So the probability of getting 0 would be 1/5. The probability of getting 1 would be 2/5. Of 2 would be 3/10. Right? Of 3 would be 7/100, and 4 would be 3/100. Okay? Where X is the number of dogs in a home. Okay? So if we go to this town and we want to find a probability that a home we select at random has 2 dogs, that would be 3 out of 10, or 3/10. So if we can use this probability to calculate the probability we've been calculating, okay, but it's all in front of us this time. We're really not inventing stuff like we did last time. So we want to find a probability that X equals 1 or 3. Okay, so we go to X equal 1, we get 2/5. We go to X equal 3, we get 7/100. Since the key word here is or, and you can't have 1 dog and 3 dogs at the same time, they're mutually exclusive. So we're just going to add up the individual probabilities, 2/5 and 7/100. That'll give us 47/100. Okay? Or 0.47 if we want to look at it that way. Now, to be a probability distribution function, X has to be numeric. That kind of got cut off here at the bottom. Each probability has to be between 0 and 1. And if I add up all of the probabilities, it has to add up to 1. Now, some things people get confused about here. First off, the X's can take on any value. The probabilities can have to be between 0 and 1. They can include 0 or 1. The probabilities have to add up to 1. The X's don't have to add up to 1. Just the P of X part does. Okay? Any questions so far? So there are a couple sections that are optional here. Section 4.2a, this deals with means, variances, and standard deviations done by hand. You don't have to do this section. However, I'll write the formulas out and work through an example or two, okay, just so we know where everything comes from. So first off, the mean is sometimes called the expected value. Expected value means that's what we expect That's what we would expect if we ran the probability distribution over and over, if we ran rather the probability experiment over and over again. What do we mean by expect? That's the X value or random variable value we would expect. The variance is the sum of the difference between X and mu squared times the probability of X. Then the standard deviation is the square root of that. So I have a short example here where we work out. So this scenario, so I have X can be 0, 1, or 2. The corresponding probability for 0 is 3/5, for 1 is 1/4, and for 2 is 3/20. Okay, sloppy 3 there, I realize. So I'm going to calculate by hand the mean, the expected value. So I take X and multiply it with its corresponding probability. So I'm going to take 0 times 3/5 plus X times the corresponding probability, 1 times 1/4, plus X times the corresponding probability, 2 times 3/10. So that's what you see here. So that's going to add up to 1/4, 6 plus 6/20 because this part's going to drop out, multiply by 0, and we get 0.55. So that means that if we were to run this experiment over and over again, whatever it would represent, we would expect an X value of between 0 and 1 on average. Okay. The variance is calculated by adding a couple of columns or doing a few columns. So we write our X's, we take X times the mean. So we're going to take X times 0.55. We're going to square that answer. We're going to multiply the answers here by the probability of X and then add it up. And that gives us 0.5475. Square rooting that gives us the standard deviation of 0.7399. So if you wrote that as 0.74, if the direction said 2 decimal places, that would be great. If it said 4, you'd have to write it that way. Okay? I think most of our answers in this section deal with 2, 3, or 4 decimal places in the directions. So mean expected value meaning is if we run the experiment, this is important, that's why I'm repeating this over and over again. If we run the experiment over and over, the X random variable value we can expect is mu, or the expected value. So we roll a fair 6-sided die, find the expected value. So first off, writing out our probability distribution for rolling a 6-sided die, our outcomes can be 1, 2, 3, 4, 5, or 6. And if it's fair, then each outcome has equal probability. It's equally likely, as we said. So if it's fair, the likelihood of rolling a 1 would be 1/6. 2 would be the same. In fact, all these would be all 1/6. So then if I calculate the expected value, I take the X times probability, 2 times probability, because 2 is an X, 3 times probability, because 3 is an X, and 4, 5, and 6, all multiplied by 1/6 and added together. This gives us 3.5, which means if we roll a die over and over again, we could expect an outcome on average of between 3 and 4, or 3.5. Any questions? So 4.2b is required. Okay, this is the part I want you to focus on. This is using your calculator to calculate expected values and to calculate, in particular, standard deviations. But if we know the standard deviation, we can square it and get the variance if we have to. So the first thing we do, if we're going to use the calculator to calculate these 3 values, is we clear list 1 and 2. Okay, we should know how to clear lists because that's a big part of the first section, or the first module, if you will. The X values go in list 1, the corresponding probabilities go in list 2. After that, you press Stat, right-hand arrow over to calculate, and enter, because we're going to choose the 1-var stat, so all we have to do is hit enter. One of 2 things is going to occur. Okay, this first one that we see at the top here, the input list could be list and then colon, frequency, then colon, and then calculate. So you need to put L1 where the X's are into list. Frequency list, you need to put L2 where the probabilities are. And then you need to highlight calculate and press enter. Okay. Another situation that could occur, depending on the age of your calculator, if your calculator is a little bit older, okay, you're not going to see this list. 1-var stat is going to appear on your home screen. If that's the case, type second and 1 in, it'll output L1, and then press the comma key. The comma key, some of you asked me the other day where the comma key is, or last night where the comma key is. The comma key is right above the 7. So press the comma key and then second and L2, or 2 rather, and that gives us L2. So it should say when you're done, 1 var stats on your home screen, L1, comma L2, and then press enter. You get the same answers. Okay, so let's look at an example. Okay, an example. This is a payout if you buy an extended warranty. So the payouts if you buy an extended warranty, the first one is you buy the extended warranty for apparently $35 and you get no payout. You don't need it. So you lose the $35. So that's minus 35. Another possible scenario is that you could get $80 above and beyond the $35 you already spent. Okay? And then the third scenario for an extended warranty is you have replacement, $175 above and beyond what you already spent. Each corresponding probability is there. We can see the probability of just paying the $35 and never using the extended warranty is the most likely at 0.992. Getting the $80 in return after we pay the $35 is 0.005. And complete replacement is 0.003. A lot of people, they'll buy an extended warranty or they'll buy an insurance plan with their cell phone. This is kind of how this is kind of how it works. Okay, so I'm going to put in to L1 the X values, and I'm going to put into L2 the Y values. The probability values. Then I'm going to go to 1 var stat, like above, by pressing the right-hand arrow to calculate and enter. And then I'm going to put the appropriate information in, depending on what scenario I have. If I have the list, I put L1, then frequency list L2, highlight, calculate, and press enter. If it goes back to your home screen, then you press second and 1, comma, second and 2, then enter. Either way, since this is money, I'm going to round both to 2 decimal places. We get an expected value, a mean of minus 3378. And the standard deviation is represented with the sigma symbol here because everything's a population when we talk about a probability distribution. And that's 1403. So what does the mean of minus 3378 mean? The mean rate of return when purchasing this warranty is a loss of $33.78 for the customer. So every time I purchase this warranty, this extended warranty, every customer on average who does this is going to lose $33.78. Okay? Conversely, okay, the company that sells it to you gains $33.78. Okay? Any questions about that? Okay, now, that was general information about probability distributions. Section 4.3 deals with a specific probability distribution. It's called a binomial probability distribution. Binomial means 2 outcomes, only 2 outcomes. So 4.3a is not required. It's a good section. There's nothing wrong with it, just not requiring it. But 14, or I'm sorry, did I say 14.3? I meant 4.3a. And then 4.3b is required. Okay, so what is a binomial? A binomial has 2 outcomes. Each time we run the experiment, it's called a trial. It's denoted as lowercase n. The result of any trial is independent from the next. So in other words, tossing a coin. Tossing a coin is binomial. I either get head or tails. Okay? Say I'm going to toss a coin 10 times. So that means that I have 10 trials. Okay? If I get ahead the first toss, the probability of getting ahead the next toss hasn't changed. So everything is independent. Each time I toss it, the outcome is not determined by the previous outcome. Okay? Since there are only 2 outcomes, this part sometimes bothers people. Since there are only 2 outcomes, right here at the top of the page here, since there are only 2 outcomes, one outcome is called a success, the other is called a failure. Now, the reason they call success and failure isn't because one is good and the other is bad. It just has to do with trying to differentiate the 2 in the most extreme possible way. So I could say tossing a coin and getting ahead is a success, and tossing a coin and getting a tail, that would be a failure. That doesn't mean one's good and the other's bad. It just means that we need to label them, just differentiate them. And the way we do this is the most extreme way, success and failure, because you can't get two words that are very different from each other, more different than success and failure. The probability of a success is denoted as lowercase p. The probability of a failure sometimes is denoted as lowercase q. X is the total number of successes in n trials. Hang on a second. So X is the total number of successes in n trials. Okay. Q is sometimes what we call the complement of P. So it's 1 minus P. So if I want to know what Q is and I know P, then I could just take 1 minus P. Now, in the first section, there's a formula approach. I'm not going to make you do the formula, but I want to show you how it's done at least once in your life so you can say, yeah, I've seen that formula before. And this is what we call the combinations formula. So this would be n choose x. Okay? This exclamation mark doesn't mean we say n excitedly. It means factorials. That means everything from n down to 1 all multiplied together. Okay, so it's n factorial over n minus x factorial times x factorial times the probability of success to the x power times the probability of failure to the n minus x powers. That sounds really difficult and it's cumbersome, but once you get used to using it, it's really not that difficult, even though you're not going to have to use it. I want to do one. So n equals 5. The number of successes we're going to have in 5 trials is 3, and the probability for success for any given trial is 0.35. So what's the probability that x equals 3? X equals 3. So n is 5, so 5 factorial over the quantity 5 minus 3 factorial times 3 factorial times 0.35 to the third, because x is 3, and 0.65 to the 5 minus 3. Where did I get the 0.65? From 1 minus 0.35. So doing some math here, knowing that 5 factorial means 5 times 4 times 3 times 2 times 1. I'll write that out. 5 minus 3 is 2, so 2 factorial is 2 times 1. And then the 3 factorial I have here would be 3 times 2 times 1. Since this is a fraction, I'm going to reduce. 3 times 2 times 1 cancels with 3 times 2 times 1. Okay. This 2 times 1 I have here, I cancel that with part of the 4. Give me just 5 times 2 in the top and a 1 in the bottom. So that's going to be 5 times 2, or 10. So that's where this 10 came from. And then I get my calculator out and I take 0.35 to the third. I get rounding 4 decimal places, 0.0429. I take 0.65 to the second. Rounding 4 decimal places gives me 0.4225. And I multiply it together. And I get about to 3 decimal places, again, depending on what the directions say, 0.181. Any questions? Now here's what you do have to do. Okay? You're going to have to use the binomial distribution function. The binomial distribution function is under the second function of the vars key, which is called the distribution menu. If you look on your calculator and locate the vars key is right under the arrows, right next to clear. And above it, it says distir. That stands for distribution. Now, there are 2 types of binomial distribution functions we look at. There's a PDF called a probability distribution function, and there's a CDF called a cumulative distribution function. So here's the difference between the 2. The PDF is used when x is equal to a single number. The CDF is used when we have a less than or equal to, or sometimes a greater than or equal to, but especially when we have a less than or equal to. So since this first question that we just did, want to find the probability that x equals 3, is a single number exactly equal to 3, I'm going to use the binomial PDF. So I'm going to press second in vars, and I'm going to arrow down to binomial PDF. Don't get the 2 confused. Okay? And then I'm going to put in the following way. If this binomial PDF, after you press enter, shows up on your home screen, you put in the number of trials, so you'd put 5 in, then the comma key, then 0.35, because that was P here, then the comma key, and then whatever x is equal to, so that'd be 3. And then press enter. If it shows up on your calculator like this, where it says trials, P, X value, and paste, then you put 5 for trial, because that is our number of trials. P is 0.35, X is 3, and then paste. Either way, after you press enter, you should get 0.81. Now, this is a different question than I have up here. This says when X is less than or equal to 3. This says when X equals 3. So what the binomial CDF does is it adds up everything from 0 to this number, whatever number I put in for X. So in this scenario, I'm going to do everything just like I did in the first example, except I'm going to use the CDF. Okay? I'm going to use the CDF. So this should say actually CDF. Right here, there's a typo there. That should say CDF. Actually, it's a misprint, I guess. So make sure you put CDF there and not PDF. So I'm going to use the binomial CDF, okay? And I'm going to do it the same way, except it's going to have a C here instead of a P, 5.35 and 3, and then paste, or binomial CDF, and it's going to be 5, comma, 0.35, comma, 3. And you should get 0.9460. So that means if I added the probability of 0, 1, 2, and 3 together, that's what I get. Okay. So let's end this with a couple of problems. Okay. First off, let's look at a new problem. If 75% of Applebee customers purchase an alcoholic beverage and 15 customers are selected at random, find exactly 8 customers order an alcoholic beverage, at least 10, in between 7 and 11 inclusive. So let's look at part A. So since part A is exactly 8, we're going to use the binomial PDF, where n is equal to 15. P is 0.75, and X is equal to 8. When we do that, depending on the syntax of the calculator we have, we should get 0.0393. Now you might want to verify these and see if you get these. Okay. For part B, at least means between 10 and 15. It would include 10. If it said more than 10, then I would have to start at 11 with the binomial. And so that means we could take each one of these, we could do the binomial PDF for 10, write down our answer, do the binomial PDF for 11, write down our answer, and so on, and then add it all up. A slick way to do this, though, would be that use that idea of the complement. So in other words, what's the complement of between 10 and 15? Well, that would be between 0 and 9. That is exactly how the binomial CDF works. It starts at 0 and goes up to a number. So we could use a binomial CDF, whichever one doesn't matter, we're going to get the same answer. 15 trials, 0.75 for P and 9 for X, and we should get 0.1484. Then we're going to subtract that from 1 because that's the opposite of what we wanted, and that should give us 0.8516. So either way, you could do one at a time, add them up, or you could do that fancy way. I don't care. It doesn't matter how you get the answer. Just get it. And then the last one, between 7 and 11 inclusive. Between 7 and 11 inclusive means, what the word inclusive means, it includes the endpoint. So it includes 7 and 11. And so what I would do is I would just probably use the binomial PDF, find the answer to each one of these one at a time, and then add them up. Exclusive means that it would not include whatever the endpoints are. So if it said exclusive instead of inclusive, it would not include the 7 and 11. So then we would just look at 8, 9, and 10 in that case. In probability notation, inclusive means you have an equal someplace along the way. Exclusive means there's strict inequality, less thans or greater thans. And then the last thing I want to talk about is the quickie formulas we see for binomial distributions. The mean or expected value is just the number of trials times P. So in this case, for the Applebee's problem, it'd be 15. We have 15 trials, 15 people, times P, which is 0.75, or 11.25. The variance, N times P times Q. So it's N times the probability of a success times the probability of a failure. Now, these shortcut formulas only work with a binomial. They don't work with a regular probability distribution. And so then the variance would be 15 times 0.75 times 0.25. Remember, Q is 1 minus P. That gives us 2.81. And we can take the square root of that, and that gives us a standard deviation. Okay, so for the binomial, since there are only 2 outcomes, those formulas are very much simplified. Any questions before we call today? All right, thanks for coming. We will see you next time.
I had a question.
Sure.
For the exam, you said 4.2 and 4.3 A and B is not included.
So 4.2a and 4.3a are not included.
Okay, all right.